Hello everyone, Mr. John here from Areteem Institute with our follow-up to last week's video where we're talking about the Four Color Theorem and really giving a little bit of an introduction to graphs as well. Now, a little bit of review, right? The idea of the four coloring theorem comes from coloring maps. So here we have a small example from last week's video. And the main idea then was when we had a map like this, mathematically, we can turn that into a graph. Now, I'm not going to redraw the whole thing, but remember our idea from last time was, and we'll do a simplified version here, all of those states become what we call vertices. So we have those vertices there. And then there are edges anytime there's a connection between those vertices. And here, a connection in the map means these states have bordering places between them there. All right, so if we look at this part of the graph, right, anytime that there's a border between those two states, we draw that graph in between. And this is a little bit more abstract, right? These vertices could be moved around, things like that as well. But that general idea then is as we have here. Every map is what's called a planar graph. So graph, collection of vertices and edges. Edges are those connections between vertices. And a planar graph is one that can be drawn so that no edges intersect. Remember, the drawing portion of that is important. We did the example last week where if we had these kind of crisscross vertices here, right, you could translate that into, well, if we kind of swap the top two vertices, we get to this general square in that case as well. So it's important that we have this can be drawn. That's a little bit different than you might originally think of it from that map perspective. Now, given a graph, where do the coloring things come in? Again, this is nothing new, but just want to start introducing those terminologies. Chi of G is the minimum colors needed so that each vertex can be given a color different to any vertex it's connected to by an edge. And in this way, we can state the four color theorem as a statement about this chromatic number. The four color theorem says any planar graph G. There's a little caveat I want to bring up here. A lot of the times when you're thinking about a graph abstractly in mathematics, there are scenarios where it makes sense for this self loop to happen. So when we say this no self loops here, we mean something like this picture we have up there. There's no way that a vertex is connected to itself, because of course that just breaks things immediately. But if we have a planar graph, then you can color it in four colors. That doesn't mean that chi of G is 4. It means that chi of G is less than or equal to 4. So that's the four color theorem there. Now, we wanted to explore this a little bit in the questions from last week. And these are actually all building to something we'll talk about in a little bit there as well. So come up with planar graphs that have chromatic number 2, 3, and 4, and try to make these graphs as simple as possible. Now, there's a lot of ways to do this, but let's look at ones with 2, 3, and 4. And getting into the ideas that we'll see on question 2 as well. Okay, we need a graph that can be two-colored. Well, if we want this to be as simple as possible, what if we just have two vertices and then we connect those vertices with an edge? So that would work there. That would give us this graph that is two-colorable One side is one color, the other is the second color. And because there's an edge, right, you have to use two colors. Now, what about this next one, right? Minimum number again. Well, if we need three colors, we're going to need three vertices. Now, what if we just connect all of those vertices here as well? So if we connect all of them, right, if we use a first color, then, oh, we have to have different colors for the next two vertices, and everything kind of is good to go from there. Now we're starting to maybe see a pattern here. What if we need four colors, right? So what if we had four colors? Well, then we need four vertices in this case. And a good way to ensure that all the vertices need to have different colors is, well, what if we just make sure that all of those vertices are connected to the other vertices there? So we have a graph that looks like this. Quick review of the planar stuff. Is this graph planar? Well, actually the answer is yes, because if I remove that last edge I drew, remember, an edge is a connection between the two vertices. What if I instead draw that connection around the outside there? That is the same graph. Every vertex is connected to all of the other vertices. We have the same setup there, and so that would show us that graph as a planar graph in that case. Now, I want to point out that these things, right, aren't unique. There's nothing really special about these setups. For example, if we went back to our square, if we just drew the square without the added diagonals, that would be an example of a graph with a chi of g is 2, right? You can alternate colors around that graph, red, blue, and it works out okay. So things like that are fine. You can do that type of stuff. There are different types of graphs that show up there, right? And this should be pretty obvious, because if we think about that triangle again, another easy way to think about this is, well, what if you just start building on to that triangle? So that graph right here needs three colors. Well, what if we just add a couple extra vertices out from there, right? And then maybe even put another triangle on the bottom, right? There's all kinds of things you can easily do to add to these graphs that don't necessarily change the chromatic number, don't change how many colors are needed when you're doing this color. And it's pretty easy to see or start to understand why some of these proofs might be complicated, right? If you remember from last week, the proof of the Four Color Theorem has like over 1,000, I think 1,600 something cases for verification, at least when it was originally proved, things like that as well. Now, let's talk here about what about chromatic numbers 5 or larger. Now, actually, this question is going to be simpler than it seems, because actually this idea that we've already come up with will work here. So what if we had 5 vertices? Well, okay, or what if we want a chromatic number 5? Then we're going to definitely need 5 vertices. Or what if we want a chromatic number 6? We are definitely going to need 6 vertices. And further, right, if we're using that number of vertices, we need to ensure that all the vertices have different colors. What was our idea of doing this? Our idea was, well, what if we just draw the vertices and all of the possible diagonals? So we start with our pentagon, we draw all the diagonals, we start with our hexagon, and we draw all of the diagonals in there as well. Right, so we have all of these different diagonals going in that scenario. Want to make sure I'm not missing any. I think I have all of them there in all of these in that case. Right? So it should be pretty clear then that we have these examples of a graph with chi of the graph is 5, chi of the graph is 6 in that scenario. Now, what's not necessarily obvious is that these are non-planar. So you might want to go back and double check this. You can, right, go through, try to move around those vertices, try to draw a connection of the vertices there if you have 5 of them so that there's no overlaps, right? Remember, we could move some of these. So for example, if we wanted that edge not to intersect, we could draw it outside of there. But you'll quickly see that even if you try to do that with some of them, eventually you're going to run into problems. This isn't super easy to prove. In fact, right, once you prove that the 5 vertex one is non-planar, it should be obvious that the 6 vertex one is, because that inside of the 6 vertex one, if you just deleted one of those vertices, you'd still have the 5 vertex one. And that's getting at some of the more complicated things going on here. Now, last thing I want to introduce. These graphs that we've done, even for question 1, have all had a similar format, right? These are called complete graphs. In fact, they would have a notation for this. This graph would be K5. This graph would be K6, right? And they are called complete graphs. Where does that name come from? Well, right, as long as we're not adding self loops, right, where things are connected to themselves, or you're not allowing, and this is typical for most graphs, you're not allowing multiple connections between vertices. This is all of the edges you can draw, right? You have your 5 vertices, and there is an edge between any 2 vertexes. Same with the 6 vertices there. So these are called complete graphs in that scenario. So K5 is the first complete graph where we have this chi of g bigger than 4 in that scenario. Now, I want to give a little bit of a bonus thing here before we end, and that is another type of graph. This is a family, so you can try to guess and figure out what the different numbers mean in this scenario. But let's do this example K33. This is what's called a complete bipartite graph. So our K33, and right, let's spoil this a little bit. So we have 3. That stands for 3 vertices, right? And then we have another 3 vertices there. And our edges, right? Where do these complete bipartite graph names come from? Well, every one of these vertices on the top is connected to the bottom. And every vertex on the bottom is connected to the top. So we have all of the edges in this case, except all of the edges means in these 2 parts. One part is connected to the second part, and things like that there. Now, what is interesting about this? Why do I want to end with this kind of question here? Well, first of all, if we stick with our coloring, we have chi of g is going to be 2. fairly clear about that, right? Because, well, what if we color, say, all of the top vertices black and all of the bottom vertices white, right? We have, okay, the top is only connected to the bottom. The bottom is only connected to the top. So as long as we color those differently, we are perfectly fine there. Now, the other interesting thing about this, so this is our coloring there. The other interesting fact that I want to mention is that this graph is also non-planar. So the graph is non-planar, but its coloring is still 2. So we need to be a little bit careful. This isn't the only way you can get non-planar graphs is by looking at these complete graphs. There are also these complete bipartite graphs that come into play there as well. So there's a lot of other interesting stuff you can cover with graph theory. Let us know in the comments below if you want to hear more about that. Otherwise, that will do it for this week's video. Give it a like if you enjoyed it. Subscribe to our channel for updates. It really helps us out. Otherwise, I hope to see everyone back next Thursday where we will dive into a new topic then. Thanks for watching. Goodbye.